Okay, here we go. We have another unrehearsed version of jungle jargon studies. So yeah, the variable speed of light is demanded in cosmology. It's not only essential; it's an absolute requirement in cosmology. Otherwise, you don't know what you're looking at. You can't possibly understand what you're looking at if you don't understand general relativity, which requires the variable speed of light. So let's get into it. Let's look at another video. I just had a live stream with another video, but let's look at another video. Maybe that video is wrong. Maybe I was wrong. Let's look at another video. So here we go. Yep. Let's get into it. Let's get started.
Welcome to Real Physics. Today I'm talking about variable speed of light, which is one of the most interesting and underestimated ideas of theoretical physics. And today I'm talking just about the history. Why I think it's so important? Well, general relativity is believed to be maybe the most important theory of physics, and it is based on the equivalence principle. Just a brief recap. The equivalence principle says that you cannot distinguish whether you are in an accelerated frame or if you are in a gravitational field on Earth. So Einstein developed this.
It'll get better. Don't worry about that.
Duncan experiment in 1907, and
what did he say? He said a Gedanken experiment. That's what I wanted. That's what I wanted him to say.
Are in a gravitational field on Earth. So Einstein developed this Gedanken experiment in 1907.
The Gedanken experiment in 1907. There you go.
And he deduced that if you are in an accelerated frame, a light ray coming into that chamber would be curved. And so a light ray has to be curved in a gravitational field. Now, how do we realize that? Well, it's a well-known effect of classical optics. And he said that could be realized if the speed of light is reduced in the vicinity of masses. And so he said in 1911, from the just proved assertion that the speed of light in a gravity field is a function of position, it is easily deduced from Huygens' principle that light rays propagating at right angles to the gravity field must experience curvature. So, variable speed of light is Einstein's very first idea when he started to think about general relativity. So you find this mentioned a lot of times in his notebooks. Just look here at the metric tensor also. Actually, the first idea goes back to 1907.
Okay, so this video is going to go through a number of different people, a number of different times that people separately came to the same conclusion, myself included, without even knowing anything about Einstein or anybody else.
Paper about the principle of relativity and the conclusions drawn therefrom. And there you find relation to the gravitational potential in this paragraph, influence of the gravitational field on clocks. He further developed the theory in 1911 about the influence of gravity on the propagation of light. And yeah, there are several papers on these topics, speed of light and the statics of the gravitational field in 1912. And then he also addressed the criticism that this would contradict special relativity. So I think this is in first place a misunderstanding of language.
Yeah, it's not that it doesn't contradict. I mean, not that it contradicts special relativity. It's just that special relativity has to do with speed. Special relativity has to do with speed. General relativity has to do with the amount of gravity, which is a big difference, and you have to understand the difference.
Because if you talk about the constancy of speed of light, it's constant with respect to the motion of an observer. Okay, that does not change the speed of light if you're moving or towards a frame. But this has nothing to do with the possible spatial variation of the speed of light, which actually can explain gravity. So yeah, he continues to talk about the that the constancy of the speed of light cannot be maintained if the gravitational potential itself does not vary.
The constancy of the speed of light is valid only when the regions are constant, or they have a constant variational potential. In other words, the speed of light is constant only locally. The speed of light is not constant over larger distances, great distances, distances between galaxies. The speed of light is not constant. The speed of light is only constant locally when you have a fixed measure of time and distance.
And he also starts to consider the Poisson equation, which is a differential operator, which is, so to speak, a precursor of the Einstein tensor. And you have also in this paper the first appearance of the idea of c-squared of the gravitational potential, because he considers the derivative of c-squared, which is c times gradient of c. And well, all this happened in Prague when he was a professor there. And then he returned to Zurich and met his friend Marcel Grossmann. And Marcel Grossmann introduced him to Riemannian geometry and said, this is very interesting, and maybe this is a tool where you can describe your theory. And it's very interesting mathematics, and there are tensors and connections and metrics and Riemann several curvature tensions. I have no problem with this. But the question is this really necessary, or can you describe relativity on the basis of a scalar variation of the speed of light?
See, I didn't need to know any of this math to understand that the speed of light is variable. It has to be variable because if general relativity is true, and it is observed to be true, clocks run at different rates, gravitational waves have been detected and verified, which means distance varies depending on the amount of gravity. Because of the interferometer, where they detected gravitational waves from collisions of black holes, neutron stars, and everything like that, it wasn't verified until the neutron stars collided, and then they were able to visually observe the collision, because when black holes collide, you can't see any collision. But when the neutron stars collided, they call it kilonova, then you can see the explosion. They saw the explosion, they verified the formation of heavy elements and everything, but they saw the explosion when they detected the gravitational waves, and they pointed their telescopes and everything at the location, because they verified the location by way of because there was more than one interferometer. So they verified the location with multiple interferometers, and they identified the exact spot where the explosion was, and they validated the fact of the variation of gravity, meaning that gravity is, distance, the variation of distance, that distance changes. The measure of distance changes. They verified and validated with the interferometers and gravitational wave detection.
And as I said, he switched over, so to speak. He gave up on the scalar theory and developed this draft theory of the which was a precursor of the then well-known general relativity. But even when doing so, even when dealing with the ideas of Grossmann and Riemann geometry, he still mentioned the dependency of the speed of light of the gravitational potential, as you can see from this paper. And well, the spatial variability of speed of light, he does not really distance himself from this very first idea. That's also obvious from a talk in Switzerland in 1930. The speed of light is not a constant, and so on. If we are forced to generalize relativity, we have to put in question this principle of the constancy of the speed of light. Well, then the Entwurf theory, the draft theory, turned out to be wrong, and he came up with the idea of general covariance, which is a technical term of the geometric formulation of Riemannian geometry. And then also David Hilbert worked on this theory, and in 1915, in November, the breakthrough came, and he managed to formulate what is known as Einstein's equations, Einstein's field equations. And this was an important step because he could explain for the first time the perihelion shift of the planet Mercury, and everybody was enthusiastic about this mathematical approach, even if few people understood it at the time. And but he did not get famous immediately. This was in 1919, after the legendary excursion by Sir Arthur Eddington, who was able to measure the light deviation.
Yeah, Sobral and Príncipe. Sobral is in Brazil. Príncipe is probably an island belonging to Portugal.
From when light passed in the vicinity of the sun. And this was a big triumph for Einstein's theory. He became a celebrity overnight. The New York Times had the headline, "We have a new Newton." And that's so to speak, the birth of the myth of general relativity in 1919. So the question remains, why did he give up on variable speed of light?
And I'm not so sure he actually gave up on the variable speed of light, because he just keeps talking about it. Because I mean, it's an innate part of general relativity. You can't dispense with the variable speed of light in general relativity. It's part and parcel of general relativity. You can't get rid of it. That's why everybody's coming to the same conclusions multiple times, multiple places, without even knowing about the other person's discovery, myself included.
Said he switched from to the geometric formulation when he came to Zurich, but that was at a time when he only considered a variability of timescales and not length scales. So, but the simple equation C equals.
See that? I keep on emphasizing it's not just the variation of time, it's the variation of distance, length scales. Because both of them compound to exaggerate the change in the speed of light.
F times lambda tells you that, well, you might consider both entities to vary, but he didn't realize that also in the draft theory was not in there. But then in the formulation of 1915, then also the variation of the length scales was included, and that's why this theory works and the other one not. So the difference is not so much describing general relativity with variable speed of light or with that geometric formalism of Riemannian geometry. The difference is if you consider just the variation of timescales, or if you take into account also a variation of length scales. And actually this...
Right, you have to take into account both the variation of time and the variation of distance, which I keep on harping. And, here they are talking about it.
This was discovered only in much later, in 1957, by Robert Dicke. And he demonstrated that you can reproduce all the classical tests also with variable speed of light, and discovered that for the first time. But however, it's worth mentioning that Einstein had great sympathy for the scalar theory, even when he was already working at the geometrical theory. He said, can the gravitational field be reduced from a scalar? Given such a complicated theory, we have to ask ourselves whether deriving gravity from a scalar is the only reasonable and justified point of view. And then he dismissed this, giving a wrong counterexample. Yeah, this is another historical detail why he gave up on variable speed of light, at least in this explicit form. But he...
Yeah, and of course he kept on thinking about it. How can you
give it up? You can't give it up because it's part and parcel of general relativity. it's not true that he liked so much this so-called geometrization of general relativity as it is discussed in this paper. And interestingly, even after the big breakthrough in 1950, he still discussed the variable speed of light. He said the law of constancy of the speed of light in vacuum cannot claim unlimited validity. It's only valid if you have a constant gravitational potential, of course, which is not true if you're...
Okay, if you didn't get it yet, the speed of light is only constant if the gravitational constant is constant. If the gravitational potential is constant.
Close to the sun, for example. And even after 1990, in Nature manuscript from 1920, you find this one. The constancy of the speed of light no longer holds according to the general theory of relativity in spaces that have gravitational fields. As a simple geometric consideration shows, the curvature of light rays occurs only in spaces where the speed of light is spatially variable. Okay, so what we know today is that indeed variable speed of light is an equivalent description of general relativity. You can either describe it with curved space and a constancy, but you can also say, okay, space is flat and I have a variable speed. There's no...
Okay, this is a good diagram here because this gives you a correct idea of what's going on in general relativity. You notice it looks like a spider web. This spider web is very important, very significant, because each one of these squares here are the exact same size and exact same distance. Whether they appear to be or not, they are the exact same size, the exact same distance. So what happens when you go through an area where there's more gravity, the distance is going to be more contracted such that you are going to pass through more frames of reference here than you would over here. So if you count them up, you go over here, it'd be 1, 2, 3, 4, 5, 6. But if you count them here, it'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. This is the reason why, or one of the reasons why, it's only the contraction of distance. It's not even considering the dilation time, because time slows down too. Besides the fact that distance contract, time contracts too. I remember trying to explain this to Steve McRae one time in Philomena, and they were just like laughing at me. They couldn't understand anything, or they didn't want to understand. But this is very, very significant because it's not just the contraction of distance, it's the slowing down of time, because when it goes through here, it slows down time too. The result is that light going through here is slower than light going through here. I mean, it's so simple. It's if you understand shapes and sizes and mechanical things and geometry, it's so simple. But people, I guess people just don't even take the time or don't have the interest or take the time to even think about it.
Difference in both cases. You can also set up metric tensors and so on and so on. There are also people who have discovered this variable speed of light in almost all textbooks on general relativity. Yeah, that's interesting. If you look closely, it never disappeared. And yeah, well, if you look at the history of the variable speed of light, we should give due credit also to other people like Max Abraham, who had a discussion with Einstein in 1912. And these are some details on that topic. And then there are other attempts like Harry Wilson, I think in 1921, made up a theory of gravitation which is very similar to these ideas. And interestingly, also Erwin Schrödinger, when thinking about cosmology in 1925, related the gravitational potential to the square of the speed of light, as Einstein did back then in 1907 for the first time. I will make a...
See that? So it's implicit in cosmology. You can't get away from it in cosmology.
another video on this because it has very interesting relations to Mach's principle. And also this cosmologist Denis Sharma speculated about the square of the speed of light being related to the gravitational potential. And of course, Robert Dicke in 1957 discovered that not only frequencies but also wavelengths are dependent of the speed of light. And that was the key insight to describing all classical tests of relativity. Interestingly, Robert Dicke did not know about Einstein 1911. Okay, I couldn't.
So here you have another example of somebody didn't even know about Einstein and came up with the same conclusion. I didn't know Einstein talked about the variable speed of light. I didn't know this guy talked about it. But I've been talking about it for several years now.
Believe that until his co-worker Karl Brauns confirmed it to me by email. And it was literally unknown in the 1960s that Einstein had done all this work on variable speed of light. But maybe the idea is so good that it had to be rediscovered. Another collaboration of German physicists in 1960. They described.
And another thing, people ask me, well, why don't you put in for the Nobel Prize? It's like everybody comes up to this same conclusion independently of each other, not even knowing about each other. And so many people have gone before me, have been there before I ever was. So how am I going to get the Nobel Prize for that? I'm just figuring out what everybody else already figured out on their own.
The almost complete version of general relativity without mentioning Einstein, saying, okay, this is a heuristic approach to general relativity. Influence of gravitational fields on time and length scales. You find it here. Now, in the meantime, there's more modern research I will mention in other videos, but people have also proved that it's indeed equivalent to the geometric formulation. And yeah, you might ask, could it be that Einstein's first idea about general relativity was the best one, and should we go back and ponder this? Now, unfortunately, as history unfolds, sometimes good ideas got forgotten, and one of
the speed of light in the gravitational field is a function of position.
the culprits, I think, is his well-known biographer Abraham Pais, who looked for traces of general covariance and all these formulas in almost all papers. And he also mentioned the paper in 1911, which says influence on the speed of light, but he does not mention the speed of light, the variable speed of light here. Very strange. And even more strange, if you look up Wikipedia, okay, you might expect that if Einstein worked and published for 10 years about variable speed of light, and he was the founder of the idea and the father of general relativity, you might expect that Wikipedia mentions Einstein here. No, it doesn't.
No, they don't even mention Einstein. That shows you how good, quote unquote, science is, which is not science. It's pseudoscience.
No mention of his first papers. This is hilarious, and I think I will do another video about that. Well, and just to conclude with some funny aspects, what Wikipedia does mention is a faster than speed of light cosmology by another recent cosmologist who does not mention Einstein, doesn't know about probably.
See, there's no such thing as faster than the speed of light. It's not that the speed of light goes faster than what it can go. It's that the measures of time and distance change, which enable light to go faster. You're not breaking the speed of light. There's no breaking of the speed of light. You cannot break the speed of light. It's always 186,000 miles a second, except your second goes by faster, and your 186,000 miles expands or gets bigger. So what does that do for the speed? If you're still going 186,000 miles a second, the second is faster, and the distance is expanded, what does that do to the speed? Instead of going 1,001, 186,000 miles, it spreads out, more, and you're going 1,001. So it's so simple and so obvious, and people don't get it.
And well, this guy gets criticized, but guess for what? Not for having maybe a slightly oversized ego or for not having done his homework. No, he becomes criticized because variable speed of light is such a dumb idea that contradicts special relativity. Okay, and this author of this critique.
And special relativity is about speed, not gravity.
Renowned expert on relativity gives a checklist for theories you should obey if you don't want to produce nonsense. Well, if Einstein had followed his checklist, we probably would not have general relativity today. Okay, so to summarize, general relativity and variable speed of light was Einstein's initial idea in 1907 and 1911 when dealing with general relativity without varying length scales, unfortunately, which was completed much later. And it does not contradict special relativity.
Right. So Einstein was considering the fact that clocks run at different rates, different speeds. Apparently, he didn't think of or didn't put down in writing that distance always changed, or he thought that it was so minuscule that it wouldn't make much difference. But locally, it is minuscule. It doesn't make much difference. Makes almost no difference. Even the time dilation makes almost no difference. You're talking about fractions of a second difference. But it adds up. But over great distances, then the times are going to vary considerably, and the distances are going to vary considerably, both of which compound the change in the speed of light. Is the opposite effect is true too. If you're going toward a black hole, everything will seem to us will be seen to be stopped because of how slow it's going, because of how slow the the rate of time is, and how small the measure of distance is. It'll look stopped to us. But if you go away from the black hole, if you go away from the center of the mass of the galaxy, then the opposite is true. Everything looks to be going faster because time is sped up and distance is larger, which makes everything go faster. The causation is going to be a lot faster.
And it's an equivalent formulation of general relativity. So I think we are severely underestimating Einstein's variable speed of light approach, and maybe his first idea was the best one. I have written a paper in 2009.
Okay, I guess that's about it. I don't want to, we went all the way, pretty much almost all the way through his video. So he wrote a paper on it. So who am I to write a paper, It's like everybody else has already written a paper, so why should I? We're talking about the same thing, right? So anyways, there it is. The variable speed of light is an essential. It's an absolute essential. You cannot dispense with the variable speed of light. It's a part of cosmology. It's a part of general relativity. It's a part of our reality in the fabrication of time and distance, where we have a slowed down measure of time and a contracted measurement of distance. Without gravity, there is no slowing down of time and there is no contraction of distance, which is basically outside of time and space. And we know what outside of time and space is. That's where God is. It's where God dwells. We exist in his fabrication and we're inside, and we exist at a slow motion kind of existence where we're inside of time. Whereas In general relativity, even in quantum physics, everything is instantaneous. You get away from the galaxies, everything is virtually instantaneous too. That's why we can see distant starlight within 6,000 years. So, I mean, it's really not so complicated. And just go through the thought experiment, and you can see what's going on with general relativity. So you have a foot, right? This represents, let's say, 186,000 miles a second. So you go 1,001, right? That's the speed of light, 1,001. 186,000 miles a second. Now, if you expand the distance and time goes by faster, where you go on 1,001, you just increase the speed of light without changing the speed of light. That's so simple. People don't get it, or they don't think about it, don't take the time to think about it. Anyways, God bless everybody. Take care. And there's nothing to worry about. Cheer up, you saints of God. There's nothing to worry about. Nothing to make you feel afraid. Nothing to make you doubt. Remember, Jesus never fails. So why not trust him and shout? You'll be sorry you worried at all tomorrow morning. God bless you. There we go. Amen. Enjoy that. Thank you. Yep. God bless everybody. Take care and stay close to God, and God will draw near to you.